What's up guys, it's Imad Fiaz and today's video is on AQA AS Level Chemistry June 2022 Paper 2 Walkthrough Section A only. Complete Table 1. Just 1000 divided by 9, so 111.1. It says independent variable in this investigation. It's going to be your rate of reaction and how long for reaction mixture to go different colours at different temperatures. The independent variable is the temperature. Student noticed that the temperature of each reaction mixture decrease, suggests how the student calculated temperature values in table 1. Okay, so what the student did was measure the temperature at the start and at the end of the reaction and find the mean. Measure temperature at the start and at the end of the reaction and find the mean. Use data in table 1 to plot a graph of 1000 divided by T against temperature. You know what you do, you just plot your graph. Plotting 1000 over T, so 0 or 211 or 200, so 0, 20, 40, 60, 80, 100, 120, and then you plot your points and then draw your curved line of best fit, which should look something like this then. Use a graph to find the time taken for the reaction to mixture to go colourless at 60 degrees Celsius. So you go to 60, then you draw a line here, and that's around about 70, right? Where it says the time taken. So then 1 divided by 70, 0. I got 0.0142, so because 1000 divided by value here, so it's around about 70. So 0.0143 seconds. But as long as you show that there and then show 1000 divided by value, you should get the mark. Explain why small increase in temperature can cause a large increase in the reaction. Molecules have more energy greater than or equal to, should say that, required activation energy, so more successful collisions per unit time, or greater frequency of successful collisions. Question 2. Student has samples of these 4 compounds, does not know which is which. Butanoic acid, carboxylic acid, 2-methylpropanol aldehyde, 2-methylpropanoic acid, carboxylic acid, 2-methylpropanol, and alcohol. 2 of these compounds identified by simple chemical test. The other 2 contain the same functional group, distinguished using a spectroscopic technique. Describe how these 2 steps to identify which compound is which. So stage 1, immediately identifying the aldehyde tolerance region. Get that off the bat. So stage 1, identifying, I'll say instead of aldehyde, 2-methylpropanol, 2-methylpropanol. So use tolerance region, silver mirror, or you could use Fehling's solution, orange red precipitate, but tolerance region is what I like to use. Stage 2, the alcohol, so identifying 2-methylpropanol, acidified potassium dichromate, orange to green. stage 3, distinguishing the acids. So using infrared spectroscopy to distinguish the two acids, use fingerprint region of IR spectrum, look for exact match to spectra of known compounds. Question 3.1. Draw displayed formula position isomer hextuene. Underline that exists as EZ isomers. So hextuene one, two, three, four, 6, and then just fill in the hydrogens. Remember, with the double bond, carbon double bond, you lose 2 hydrogens, and those 2 hydrogens are gone. Draw displayed from a chain isomer that does not exist as E and Z isomers. Hextuene. This is position isomer, change the position of the functional group chain isomer, so it's got to be as a chain, right? So I could have, I guess, the example is I could have 4, 5, 6. I have a double bond here, hextuene. Fill in the hydrogens, but because it's a chain isomer, I could have this. Oh, sorry, I have the hex. Yeah, sorry, I have a double bond here, that's normal. CH3, so I've only got 1, 2, 3, 4, 5 carbons, right? That's gone, but then instead of that, then I've got a methyl group here. That's what I was trying to aim for. Just delete from the functional group isobutanol that has absorption in the range of that. So butanol, absorption in the range of that. So basically, butanol, methane, propane, methane, ethane, propane, butane. Perfect. And I'm just going to have a pseudo bundle here. Bundle here. Let's get formula of a structural isomer of butanol has absorption in the range this in its infrared spectrum. So structural isomer butanol has absorption in this. So it's going to have OH group, butanol, but it's a structural isomer. So I could just have it like this. OH, yeah. 4 sides. So saturated halogen alkane contain this much of bromine, carbon empirical from these compounds. So carbon to hydrogen to Br, 17.8 divided by 12 to 3 divided by 1 to 79.2 divided by the mol bromine, which I don't know, which is 79.9. Okay. Then you get your ratio, then divide by small ratio, take the empirical formula as 3 to 6 to 2, so therefore C3H6Br2. Now, are UPAC names with two such a halogen alkanes evidence empirical formula? Well, C3H6Br2 will have Br here, or on the second carbon, so it could be 1,1-dibromopropane, one 2-dibromopropane. Question 4 is question about gas volumes. Alhamdulillah, TNT is an explosive because it decomposes very quickly and exothermically to a large volume of gas. Equation for decomposition is shown. Calculate volume of gas measured at this, produced by decomposition of this much. Gas constant R is at 5 moles. Calculate volume of gas produced by the decomposition of this. So first thing I would do is moles of TNT, which is mass in grams, divided by the MR. I'm going to leave it like that. Okay. Then obviously I know I'm going to need to use PV equals nRT. I want to find out the volume, so I'm going to use V equals nRT divided by P. If it asks you, for example, to find out the MR, or the mass, or the moles, using N equals PV divided by RT. And that's something that's difficult to spot sometimes. It'll ask you for the MR and you're like, how to do that, but then you realize, okay, I need to find out the moles, then the mass, then the MR, or the moles, use the mass to work at the MR. So the number of moles, 1000 divided by 2 to 227.0. I shouldn't have included that. That looks like 2270. So 227 times by 8.31 times by temperature in Kelvin, 1250, plus 273 degrees Celsius to Kelvin. We just add 273 and vice versa, Kelvin to degrees Celsius minus 273. Or the pressure in pascals, 101,000. Now this will give me the volume, and remember, volume in the ideal gas equation is measured in meters cubed. Okay, so that will give me the volume in meters cubed. So 1000 divided by 227 times by 8.31 times by 1250 plus 273 over 101,000 pascals, I get 0.552 volume in meters cubed. Then I want to know obviously the volume of gas produced by the decomposition of this, the gas. So I don't care about this carbon, I don't care about that. So what's the molar ratio? I've got 2 here, and then here I've got 3 plus 5, which is 8, 8 plus 12, which is 20. So whatever the volume I've got here, I'm going to times it by 10. Times it by 10, 5.52 meters cubed. Find out the moles, then find out the volume, and then you can find out 5.52 meters cubed. That's how the Mark scheme used the moles of TNT, then times it by 10. Find out the moles of gas form, then use V equals nRT divided by P. But I just did find out the volume, then use the molar ratio to find out the volume of gas produced. You still get the same answer though, so it's fine. Then it says calculate volume of oxygen needed to control the complete combustion of 200 cm3 butane. Calculate volume of oxygen, and I know that that's that. Alkanes generally form that alkanes undergo complete combustion. 1 mole of this reacts with 3n over 2 moles of oxygen. Calculate volume of oxygen needed for complete combustion. This much butanene. So I've got butanene times by the number of 3n over 2 oxygen, where n clearly is number of carbons, and butanene, so it's going to be 4. It's going to be 200 times by 12 divided by 2, which is 6, which is then therefore 1200 centimeters cubed. Bit of a weird one marker, but it's fine. Question 4.3. Alkanes have general formula CnH2n plus 2. Alkanes undergo complete combustion in the plentiful supply of oxygen. Determine X in terms of N. Alhamdulillah. Well, I can see that X here. Here I've got N plus 1, N, X, 3N plus 2, 2N, 3N plus 2. Yeah, so I've got 3N plus 2 plus X equals N plus N plus 1. Is it 3N plus 2? 3N plus 2. Oh, it's 2N plus 2 of N. 2N plus 1. So I'm going to have 3N plus 1 over 2. Forget it, it's 1 mark anyway. Question 5. Obviously, if it's real exam, I'd come to this last end if I'm spending too long on a 1 marker. But yeah, it is just 1 mark. And if you don't know how to do it, just skip it. But I just copy from mark scheme. 3N plus 1 divided by 2 is N. Name the mechanism for this reaction. Question is about synthesis propane reaction. 1 iota propane, X ammonia. It's going to be nucleophilic substitution. So I've got 1 iota propane, methane, propane, X is ammonia. I know what the mechanism. Perfect. Okay. CH3, CH2, CH2. Carbon's partially positive, iodine partially negative, lone pair of electrons, NH3. Let's just show all the bonds. Attacks partially positive carbon, CI bond breaks. Then you've got, I should show it like this, but I ain't got enough. I have, but I don't want to do it there anyway. CH, NH3 replace the I, and then nitrogen's positively charged. Then lone pair of electrons and NH3 again. And instead it shows you in the equation 2NH3. So I'm going to use 2 molecules. Acts as a base, takes a proton. There you go. And then what you form is this, and obviously the nitrogen, H, lost a hydrogen, and there you go. CH3, CH2, CH2, NH2. Perfect. Nucleophilic substitution, and then another one acts as a base, 6 proton, that breaks, and then you form that. Question 5.2. One dash out of propane is a liquid at room temperature, calculating the molecules in this much. So I've got a density. I need to find out the number of moles first, and then I know it's 1.75 grams per centimeter cubed, and I've got 5 centimeters cubed. So it's going to be, the mass is going to be 5 times by 1.75 over the MR, which is 69.9. I think the hardest part for including myself, most students, is falling for the trap of density is mass over volume. They have to find out the mass is density and time by volume. Well, yes, it is. And yes, it is in this case. But it says gram per centimeter cube. You've got 5 centimeters cubed, so you need to times it by 5. How about 169.9? That'll give you the number of moles. 515. Then to find the number of molecules, all we do is just times by Avogadro's constant. So times by L. 6.022 times by 10 to the power 23. And then you get 3.10 times by 10 to the power 22. Arranging from answers. What do I get? Yeah, 3.10 times by 10 to the power 22. Then it says an experiment this much of 1-iodo propane react with X ammonia, this much propylamine are produced. Calculate percentage yield in this experiment. Alhamdulillah. Well, percentage yield is actual yield over theoretical yield times by 100 because it's a percentage, and it's only 2 marks, so I'm not going to have to do too many steps. But what I'm going to do here in this case, then, what I'm going to do is work out the moles of each. So the moles of propylamine, 2.3 divided by 59 over 10.3 divided by 169.9 times by 100. .3%. Always be wary how many marks it is. If it was a bit more, then it probably wouldn't be that easy, right? Find the moles of propylamine, find the moles of that, and then moles of propylamine over moles of 1-iodo propane times by 100, 64.3%. Question 6.1, calculate percentage atomic economy for the production of CCl3F in this reaction. So percentage atomic economy, MR of desired product, and they always like to ask about percentage atomic economy or atomic economy in general, either by multiple choice questions where it's just one marker, or actual questions, and it'll be like 2 marks or maybe 3 depending on how difficult it is. So MR of desired products, so MR of that over the MR of all reactants times by 100. That's what we need to do. So if you work out the MRs of them, which is probably the hardest part because if you memorize a formula, then you already know what you're going to do, right? And if you haven't memorized it, then you're probably going to struggle, and then you get 27.9% by doing 137.5 divided by 492.6 times by 100. Intermediate alternative phase is dichloromethane. Wait, actually, let's read the full part. An alternative synthesis is the free radical of CCl3 is F is a free radical substitution reaction between chloromethane and chlorine. Intermediate alternative synthesis is dichloromethane. Give equation represent the purification steps and the conversion of this into this. So conversion of CHCl2F plus a chlorine free radical and I'm gonna have obviously I'm gonna have a HF plus not HF, sorry, HCl in this case. Yeah, HCl plus chlorine free radical here. I should know because this hydrogen is going to bond to this chlorine and the free radical is going to go to CCl2F. Then we've got CCl2F plus excess of chlorine, and I know I'm going to form this anyway, F, and then therefore what's remaining? Chlorine free radical. CHCl2F plus Cl dot to form CCl2F free radical plus HCl, CCl2F free radical plus 2 excess chlorine to form CCl3F plus Cl dot. Give equations to represent termination step forming this compound. Show the structure formula of the product in the equation. So I'm going to go from 2, because I'm trying to show the formation of a compound with the empirical formula that. Yeah, because if you think about termination step, initiation, propagation, termination, for example, like I tell you, we've got chlorine, it's going to be Cl plus Cl dot to form Cl2, right? So in this case, termination step forming this compound, right? We'll have CCl2F with a free radical plus CCl2F, the free radical, to form C2, or actually CCl2F, CCl2F. Or you could just have a 2 in the beginning here with a chlorine free radical. But yeah, either way, obviously the arrow should be here, but I don't have no space, so therefore it's that. That's fine. In Europe, some of the glucose is fermented. Use of carbon neutral leads to no net emissions of carbon dioxide atmosphere. Justify the statement. Include relevant chemical equation. Answer for 4 marks. It's a very easy question if you just memorize these equations, which you should have. So first one, photosynthesis one, 6CO2 plus 6H2O to form C6H12O6 plus 6O2. Then I've got C6H12O6, and this process is called fermentation now to form T2C2H5OH plus, I know I'm forming carbon dioxide, but how many am I going to form? 100 moles. Well, it's going to have to be 2 because I need 2 carbon. I've got 4 carbons from the ethanol, so I need 2 there. Then I've got 2C2H5OH plus 6O2 to form 4CO2 plus 6H2O. And that's your first 3 marks by just recalling your equations. 6CO2 plus 6H12 to form C6H12O6 plus 6O2. C6H12O6 to form 2C2H5OH plus 2CO2. 2C2H5OH plus 6O2 to form 4CO2 plus 6H2O. The final mark is the idea of just a random statement, right? What are these equations representing? Well, the formation of glucose, C6H12O6, takes in 6CO2, and fermentation. So this is the formation of glucose. Then this is obviously the fermentation, like I said, and then this is the combustion. So and the fermentation and combustion of in this case then ethanol gives out 6CO2. So formation of glucose takes in 6CO2, and then that's obviously photosynthesis, and then fermentation and combustion of ethanol gives out 6CO2. Suggests why ethanol produced using silver skin from South America is less likely to be carbon neutral than ethanol produced from crops grown in Europe. The transport from South America to Europe as a you could say produces carbon dioxide, has carbon emissions, but could also say it has a larger carbon footprint. Okay, only a couple of questions left. Energy release per mole of carbon dioxide produced. Energy release per mole of carbon dioxide produced. Should get 685.5, 668.25, 595.3, and this is another weird question that I don't particularly like. And then it says use your answer to deduce fuel with the lowest environmental impact by this measure. With the lowest environmental impact, the one giving the highest energy release per mole. So in this case, 685, 668, 595, so ethanol. Because it's got the lowest environmental impact, produces the most energy release per mole of carbon dioxide produced. Calculate value for the final temperature in experiment. Okay, so final temperature of the water in experiment. So Q equals mc delta T. Delta T equals Q divided by mc. I can't find out Q because I don't know delta T, so I'm going to use delta H equals Q divided by moles. Moles equals mass over mR. Now rearrange delta H is Q divided by moles. Q equals delta H times by moles. So it's going to be, I don't care about the negative sign, 1786 times by the moles of what? The propanone. In this case is of the propanone. So 1.18 over the MR, which I can work out. It's 1786 times by 1.18 over the MR, which is going to be 12 plus 12 plus 12 plus 16 plus 16 plus 16 plus 16 plus 16 plus 16. No, that's, oh, sorry, that's 6 hydrogens here. Got confused. So just plus 6 plus 16. 36 point something, 3358627. That's Q. I want to find out delta T. Well, then it's going to be my answer to Q over the mass of what in this case? Well, that's the mass of water. And I've just rearranged the equation, so that's also the mass of water. And the mass of water is given in the table at 260. So 260 times by C 4.18. And then I get delta T. But one thing you need to notice is that because delta T, I want it in degrees Celsius, Q, right, it's got to be in joules. So I get 0.034, therefore it's going to be that times by 1000 over MC. So then, or I can just times my answer by 1000, and I get 33.4 degrees Celsius as delta T. 33.4 degrees Celsius, right? But I know there's always a trick to these parts. There we go. Initial temperature is 22.3. I don't want to find out delta T. I want to find out the final temperature of the water. So I know the difference between these two is 33.4 degrees Celsius. And yeah, so therefore the final temperature is just going to be 22.3 plus 33.4, 55.7 degrees Celsius. Slightly trickier, but yeah, it's 4 marks. Q equals MC delta T, delta T is Q divided by MC, delta H Q divided by moles, Q is delta H times by moles. Find out Q, and times by 1000, divided by MC, you get delta T, but then add from initial temperature, because I ain't trying to find delta T, I'm trying to find final temperature, and I get final temperature, 55.7 degrees Celsius. I use data to calculate value for mean carbon copper bond enthalpy in the gaseous butyl mono. I know delta H is minus 20504. Because energy required to break bonds minus energy released when new bonds are formed. So C4H9OH. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 CH bonds. So 4, 1, 2 times by 9 plus 1, 2, 3 carbon bonds, which I'm trying to find, so 3Y plus, I don't know why I'm doing that, double brackets in, new thing, plus CO 360 plus OH 463, and then I can't obviously forget about the 602 plus, well, it's going to be O10 plus 12 times by 496 minus energy released when new bonds are formed. So I've got C010, so it's going to be 8 times by 805 plus 10 times by 463. Okay, collect like terms. Minus 2504 equals what? 412 times by 9 plus 360 plus 463 plus 12 times by 496, and 10483 plus 3y minus 8 times by 805 plus 10 times by 463, 11070. Then I get 10483 minus 11070 minus 587, therefore minus 2504 plus 47, then divided by 3, I get, okay, something's gone wrong here, so I've got, something definitely has gone wrong here. Oh, it's not 12 times by 496, why did I say that? It's older 10, and I've got 6 of them. And older 10 is just 1, which is 496, so it's 6 times by 496. And that means this is also wrong. No, that's right, and then that's right, because these are 2 separate ones. That's 8, and then that's 10. So I just made a silly mistake there. So let's try that again then. So minus 2504 equals 412 times by 9 plus 360 plus 463 plus 6 times by 496, 7507 plus 3y minus 11070, because the rest energy release of new bonds of form is perfectly correct. 7507 minus 11070 minus 3563 minus 2504 plus 3563, and then divided by 3, and I get y, which is your carbon-carbon bond enthalpy, as 353 kilojoules per mole to the power minus 1. Butanol can be, butanol can be manufactured by reacting steam with butanol and in the presence of acid in the catalyst constitutes ferric acid. Butanol reacts with constitutes ferric acid to form compounds W and X. So steam with an alkene. Okay, butanol reacts with constitutes ferric acid to form compounds W and X. So it's going to be electrophilic addition, and yeah, I don't know why I took it. Just need to break that part down, because if you get that part wrong and then you start jumping in and you're doing the reverse of the mechanism you're supposed to do, then all those 5 marks is gone. So make sure you know exactly what mechanism is going on and then recall it from there. So conversion of butanol into compound W. So butanol, so methane, ethane, propane, butane, butanol, that has a double bond. Yeah, I'm only using 2 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. C4H8. Perfect. And it reacts with constitutive ferric acid to form compound WX. So hydrogen partially positive, oxygen partially negative, S double bond O, double bond O, OH. Then from the double bond to here, that to there. Perfect. Then you've got CH3, CH2, CH, CH, and then I can see that compound W is only attached to one of this, the CH2, right? And it's primary carbocation, whereas this one is secondary. So to form compound W, the carbocation is going to be here. So you got a hydrogen goes here, and oxygen lone pair of electrons, negative charge, S double bond OH, bonds here, and then what you form? You form compound W, CH3, CH2, CH2, CH2O, that's S double bond OH. So you get that. Double bond, then carbocation. Actually, the hydrogen should be here, not there, but I guess it's fine. Then carbocation. Well, if hydrogen's there, then hydrogen's here, and the carbocation's here. Then yeah, lone pair electron, oxygen minus charge, bond to the H plus, but it does want to show the formation conversion into that, so I do need to show the final step of it bonded to that. So CH3, CH2, CH2, CHHOS double bond OH. That's exactly like this, compound W, and it's attached to the alcohol, to the carbon directly at the end. That's why it needs to be like that. Instead of bonded here, it needs to be here, because you can see that in the diagram. There's a very low yield of butane 1 from but1ene in this manufacturing process. Explain why. Very low yield of butane 1 from but1ene in this manufacturing process. Explain why. Because of it's formed via less stable carbocation formed from, or in this case, it's formed from primary carbocation rather than secondary. Carbocation formed by less stable carbocation formed from primary carbocation rather than secondary carbocation. That is the end of section A.